Here's the Math117 script that you will have to modify in order to do a couple of homework problems, and I will try to explain what's going on. If you've never programmed in R at all, or even worse, if you've never programmed in anything before, you might have to get out the script and play with it quite a bit yourself in order to get a full understanding. Okay, we're going to be doing an n-step scratch ticket, and I will set up the parameters that govern this process. I need to know the price on day 0. I'll use 50. The number of steps, I'm going to use 300. My computer's fast enough that I could probably use 3,000 and get away with it. Then I need the multiplier for an up step, which determines the so-called volatility. I will use 1.04. Change that to something like 1.07 and you will see a big difference. As you recall, because the average of V and 1 over V is not quite 1, this model leads to a gradual upward drift in the prices. And if I look at this, I get a number that looks very close to 1, but the fact that it's a little bit less than 1 actually matters. So what I am going to do is store that in the variable m. Every time we take a step, the price will be multiplied by m. That will compensate for the upward effect of the random part of the prices. You can choose whatever probability you want for an up step. I've chosen 0.4, but you can change this script to get anything you want. So here are our standard variables. V is applied as a multiplier for an up step, as a divisor for a downward step. M is applied as a multiplier no matter what. So the factor by which the price changes for an up step, U, is M times V. For a down step, it's M divided by V. And if I want the price to be a martingale, you know the formula for the probability on an up step. It's 1 minus D over U minus D. We started out with 0.4 and got back 0.4, showing that we haven't made any mistakes in the calculation. The logarithm of V is conventionally named sigma. The logarithm of m is conventionally named mu. The asymmetry of the random walk is best measured by 2p minus 1, but Deneen is fond of using an approximate value for that based on mu and sigma. If you look down at the bottom, you'll see the result from his approximation is very close to the exact result. And he also does an approximation for the drift factor that agrees with 6 decimal places to the exact one. The variance in a single step is sigma squared, because the logarithm either increases by sigma or decreases by sigma. So the square of the change is always sigma squared. For n steps, I have to multiply that by n, and that's the variance of the logarithm. Okay, now let's generate a few sample paths. We will store the results in a numeric array called prices, and I have found experimentally that when you're displaying this, you want to be willing to display numbers on the vertical axis up to roughly 1 plus the exponent of n times sigma squared. If your graphs are going off the top of the screen, you may need to increase this slightly. Okay, so now I will set up a blank plot with steps plotted horizontally, prices plotted vertically, and for a wide variety of colors, I will just have the prices evolve in the way that you've seen if you've looked at my other video. At each stage, what I do is I sample from a vector that has two components, u and d, one sample where the probabilities are p for the up step and 1 minus p for the down step, and I store all these prices and plot them, and you can get an idea of the different things that can happen. People are always surprised at how jagged these paths are, but this looks like actual stock charts, doesn't it? This model is far from a perfect representation of what stock prices do in the real world, but it's a pretty good approximation. Okay, now let's see if we've got a martingale. We're going to generate 10,000 final prices, set aside a 10,000 element array to hold them, and also hold the change in the exponent. That is, we will take the logarithm of the factor by which the prices go up or down. And I'll just run through all my repetitions, and on each repetition I will generate the final price by saying initial price times the effect of n upward steps times the effect of n minus n up downward steps, and then I will take the ratio of that final price to the initial price and store its logarithm. That's now been done. If we've got a martingale, the mean value of these 10,000 final prices should be close to 50, and indeed it is. If p equals 1/2, the exponents are doing a symmetric random walk. If p is different from 1/2, they're not, and in this case we chose a p that was different from 1/2, and therefore the mean value of the logarithm of the price change came out to be somewhat negative. I can measure the variance of this, and if I take the actual logarithm and subtract off the right amount, which according to Deneen is n times mu to correct for the drift minus n times sigma times gamma to correct for the effect that multiplying and dividing by the same factor tends to lead to a net upward drift of prices, I should get something close to 0, and indeed I do. Now let's analyze the distribution of prices. One easy way to do it is to plot a logarithm. It's always surprising, even with the large number of prices that I generate and the large number of steps, how discontinuous this is, but the fact is that these are situations where you get a large number of upward steps, and if you have one more upward step, it takes you from one of these bars in the histogram to the next. If you want to remove this effect, just run this with a much larger number of steps. If I look at the median final price, I discover it's not at all close to 50, it's 40. This is a property of this binomial model and of the Black-Scholes equation. The median is always less than the mean. If we look at extreme values, notice all these nice functions in R. I can find the smallest value by taking min. One time this stock really tanked. It went all the way down from 50 down to 4. Another time it went up from 50 to 537, and when you look at that you can see why the median has to be less than the mean. There's a small probability for an enormous increase in the price, but the probability of an enormous decrease in the price in dollars, not as a percentage fact, is much smaller. Now we can actually start thinking about options. Suppose the strike price is 60. We'll store that in K, and I should discipline myself not to use equal for assignment. Sometimes it leads to the wrong result. Now this next line is a bit of an outrage. Final price greater than k. That's a Boolean expression. It's either true or false. If R treats a Boolean value as a number, it converts true to 1 and false to 0. So the mean of final price greater than k is actually the probability that the final price exceeds the strike price. What's going on here? We're just exploiting the fact that a probability is the expectation of an indicator function. And we can see this option would have a 26.4% probability of being in the money. It's easy enough to figure out the exponent we required in order to get a stock price that equaled the strike price. I just take k over x0. The logarithm of that is the exponent we need. And then it's easy enough to calculate how many up steps we need in our random walk in order to achieve that large an exponent. And I can check this by saying with that calculated number of up steps, we'll take the initial price times the effect of n upward steps and the effect of n minus n up downward steps. And sure enough, we got 60. And now R has everything you'd want to know about the binomial distribution. I can ask, what is the probability of getting that many upward steps or more? The way I get more, the probability of more than n up steps, is by setting lower tail equal to false. If I don't put this in, I will get the probability of getting a number of upward steps that's less than or equal to n up. And sure enough, we found a probability of about 26%. We saw that earlier. In fact, we can predict the entire distribution of prices. And what I'm going to do now is build up a simulation of an array of final prices. I will start out this array by giving it a first element, which is the price on day 1. And now I'm going to range through all possible values of the number of upward steps. If I have I upward steps, then the price gets multiplied by I factors of u and by n minus I factors of d. So that's the price with that number of up steps. And by knowing the probability of getting precisely I upward steps in a binomial distribution with n steps and a probability of p for an up step, I just multiply that probability by the number of repetitions, use the floor function to turn that into an integer, and add that many repetitions of the price to my array. So now what I have done is concoct an array of final prices. And here's a cute trick which I will not explain in detail to overlay one histogram on another. With these simulated prices, the histogram looks much the same. Purple means the two agree. Red or blue is something that's present in one histogram but not in the other. Okay, that should give you enough information that you can fiddle around with this and do your homework.